In order to capture all these particles flying out from this high energy collision of two protons against each other, they built this complicated device. And the reason is that they don't want to miss anything. So this kind of collision can produce all kinds of particles. And depending on the nature of particle, there are different ways of capturing them. That's why I have to put in this layer and layer of different kinds of instruments so that you can detect all kinds of particles that may come out from these collisions. You can detect electrons, protons, something called muons, and you try to make sure that you can capture all of them, measure their momentum and energy. So that's actually a very delicate measurement you have to do, even though they are coming out at the speed of light, so you can sort of contemplate the challenge associated with it. Some particles you can never detect, like neutrinos we talked about in the first lecture, because they interact so little with anything else, they will just fly away, and you don't see any the sign of it. So it will be a challenge if you produce neutrinos and you would like to know if they have been produced, and that is another subject we'll come back later. Another question you might ask is, okay, now I understand why it has to be so complicated, but why does it have to be so big? And that has to do with the energy of the particle. So the way you try to measure how quickly the particle is moving is by bending them. So what do you do is, let's say, here's an electron in this yellow line coming out from this collision. Electron has a negative electric charge. So if you have a particle with charge, if you place a magnetic field on it, it actually bends. That's what a magnetic field does. And if you can't follow this, it's completely okay. You just need to know that you need to make a big things. But if you'd like to know a little bit more further about this subject, what you can do is do a very simple math. So if you have a magnetic field applied to a charge Q flying with speed v, that's velocity, this is the force that is exerted on the particle called Lorentz force. So the particle would bend because it's pulled in one direction. And being pulled, it has to balance with centrifugal force, which goes with the mass and velocity of the particle with this formula. If you let them balance against each other, you find this equation, which you can solve now. And this r would be the radius of curvature. So if r is big, it doesn't bend very much. If r is small, it bends a lot. And in order to measure this bend, you need to make sure that this radius of curvature is smaller than the size of the apparatus. And that's hard if the velocity of the particle is big. So the bigger the speed, you have to make the radius larger, that you have to build a bigger detector. So that's why we need to build very big apparatus. And in the world of science, having only one measurement is not considered to be safe, because even though we try to be careful as much as we can, sometimes we do make mistakes, sometimes accidents happen. So there's a competing experiment called CMS. And C actually stands for compact, even though this one is also pretty big, like 50 meters high. And there was a sort of a thrilling moment when somebody came up with the rumor that they have found the Higgs boson back in 2010, when Atlas experiment even haven't started looking for it. So that was a kind of shocking thing for some people. It turned out that was a bogus rumor. What they had found was the Mr. Pigs, not the Higgs boson itself. So if you actually do have this collision of protons, it's actually not a simple matter to dig out the signal of what you're looking for. So this is a result of a single collision, because when you collide beams of protons, there are actually many protons inside a given beam. So you actually see many, many collisions happening at the same time, like 20, 30 of them. So it's a very complicated mess, as you can see. And not only that, each collision is very unlikely to produce what you're looking for. You need to keep repeating this like a quadrillion times. And among these quadrillion collisions, maybe tens of them have the signal you're looking for. So that's an incredible challenge. Modern computer technology has allowed us to do so. But again, you can sort of guess how challenging that is. So this is an example where we think that we have managed to produce the Higgs boson. Again, two protons smash against each other, produce many, many particles coming out. And then you sort out this mess to identify what you are really looking for. And at the end of the day, you start spotting something rather special in it. So you see 4 blue lines, and of course lines do not come out colored at the beginning. You have to dig out and make sure which one is important over the others. And this is the case where the Higgs boson presumably has decayed into particles called muons. And there are 4 of them. That's why we see these 4 blue lines. So this is another example of the collision of protons which we believe have produced the Higgs boson 2. So in this case, again, you smash protons against each other. So that's the condition of the Big Bang. A lot of different particles fly out from this collision. Each time you see different things, actually. And in this case, you see different particles that decayed out from the Higgs boson. And again, by shifting through all this mess very carefully, you find, again, 4 blue lines. And 2 of them show even this green blob. And that's a good sign that the produced particle here is an electron or positron. And these long lines correspond to muons. So you can tell what kind of particles have been produced. And this is the way you shift through this huge amount of data and try to identify the particles you're looking for. And even after you actually think you discovered something important, then the scientists tend to be very, very careful. So we would like to not report sort of the false signal. We really would like to be sure about what we have discovered. So there's a stringent requirement on the confidence we require when we announce a big discovery. And when you are 99.7% sure, then you say you have found evidence for something. But when you would like to say you discovered something, you would like to be sure 99.99994% sure. There's a probability of mistake only at the level of 0.00006%, and that is called 5 sigma based on this normal distribution of the errors. And so this is just a conventional choice for claiming discovery, but this has been actually kept quite well in the community of physicists. So on the July 4th, 2012, there were a series of talks presented by the leaders of this experiment, and one of them claimed 4.9 sigma when you want to have 5 sigma, and the other one did reach 5 sigma level, and that is why the people announced the discovery of a new particle they were looking for. And one of the leaders of the experiment is being congratulated by the Peter Higgs himself. So based on this incredible development, the laboratory CERN released an official statement. So CERN experiments observe particle consistent with long-sought Higgs boson. And the phrase they used is that they observed a Higgs-like particle. They didn't quite say they observed the Higgs boson they were looking for, because they are still not completely sure about the property of the particle you discovered, but at least something had been found that sort of looks like the Higgs boson. So that's the meaning of this sentence here. And especially that this was actually done and reported on July 4th, which is an Independence Day in the United States. A lot of us call this day the Higgs Dependence Day. And that was a big celebration worldwide. And so the question then is that, how important is this discovery? Why have we been looking for this particle for 50 years? Well, some people even dubbed this particle a God particle. And Leon Lederman, another Nobel laureate in physics, wrote a book titled God Particle that discussed this pursuit for the Higgs boson. And the rumor is that he didn't actually want to name this particle God particle because it's been so hard to look for this particle for many, many decades. He got frustrated and actually called this particle Goddamn particle. But the publisher didn't think that was a good idea to use this as the title of his book, shortened it, and became the God particle. But at least it conveys a sense that this particle is very important for physics and for us to understand the origin of our existence. And these people are presumably candidates for Nobel Prize based on this discovery, based on their papers they had written back in the 60s. Unfortunately, Mr. Robert Braut has passed away, but François Englert and Peter Higgs are still alive, and hopefully they will receive the Nobel Prize of Physics sometime soon. And in order to explain the importance and function of the Higgs boson that is stuck everywhere in the universe, there was a competition conducted by a UK funding agency who can explain the importance of the Higgs boson the best to the general public. And here's the artwork from the winners. So the idea, according to this explanation, is like a cocktail party. And somebody famous walks into the party. So in this picture, it's Einstein. And then crowd would gather around this celebrity, and then Einstein can no longer really move because it's surrounded by so many people. So if you remember F equal ma, being hard to move means it's massive, right? So the Einstein has acquired a lot more mass than before entering this party. So the Higgs boson is said to be the origin of mass. And apparently the UK funding agency is so generous that when they announced this competition, they actually promised a champagne to the winners. And Dr. David Miller did receive a bottle of champagne from UK funding agency, which is kind of nice. But sort of the anecdote of this story is that in the initial version, the model was actually not Einstein, but rather Margaret Thatcher. But eventually they decided to change this from Margaret Thatcher to Albert Einstein because Thatcher has slashed the science funding in the UK so badly that they didn't like to have Thatcher around anymore. Anyway, so the most important thing then is what does it mean to talk about the origin of mass? We normally think everything has mass, and that's something we also taken for granted. When we put ourselves on a scale, we measure our mass, and we always worry about maybe I'm overweight, or maybe I should eat a little bit more. So mass is something we think everything got. We never ask the question, why is there any mass at all? But in physics, when you think about this, again, famous equation E equals mc squared, mass is energy, right? So if you have a particle, or something with mass, sitting around not doing anything, but still got energy due to some reason, and that is actually very strange if you think about it. Why does have a particle just sitting around not doing anything got energy at all? So that's the question we'd like to understand. For a particle just sitting around, where does the energy come from? In the case of our body, we think we know where the mass is actually coming from. It's the kinetic energy of quarks. So let me illustrate that in a picture here. So when you look deep inside our atom, we have these protons and neutrons. They have 3 quarks inside. And these quarks are moving about pretty much the speed of light, bouncing back and forth all the time. And that's why the quarks have kinetic energy. They're always moving. They get bounced around within like 10 to minus 24 seconds. They're jiggling around like crazy. So that is the source of energy of the proton. But when you weigh protons and neutrons, you're looking from outside. You don't see the quarks inside. So the only thing you can tell is that, well, it got some form of energy. We don't know what it is. But proton itself seems to be sitting around, not doing anything. So that's what we perceive as the mass of the proton. So kinetic energy of the quarks is what we are measuring on a scale when you put yourself on it. So that story sounds bizarre. The existence of quarks had been proposed by Mr. Murray Gell-Mann, another Nobel laureate in physics. But this is the way we understand where the mass of a body comes from. It's actually the motion of quarks inside protons and neutrons. That's what we are measuring on a scale. So now comes the question, okay, that's most of the mass of our body, but there's also a little bit of mass we're missing from this picture. And that's the mass of the electron that's moving about in this picture here. So why do we need the mass for the electron? Why is that important for us? So that's the question. I leave it here, and we'll come back soon.